All right, sorry about that, guys. Nilla was being a distraction, so I got a little, distracted. Let's try this again. We want to find the position of the particle at time t equals 3, right? So let's kind of think theoretically about what's going on right here. We know the velocity. We know the velocity. We have an expression for the velocity. And we also know this is the case. If I take the integral of the velocity, right, I get the position. Let's say if I go from A to B, I'm going to get the position of B minus the position of A, right? Because the integral of velocity is position. Right, so this is a fact we should know. So let's think about what I really want to know. I want to know the velocity, the position at time 3. So I have a 3 with a velocity here, right? And then I don't know what we're going to have down here yet. So this will be position of 3 minus position of question mark, right? So if I know what that question mark is, I can fix everything I need. So I need to look at the little extra bit of information I have in the problem. And the extra bit of information is the position at time 0 is -5, right? So the position at time 0 is -5. If I put, for instance, a 0 down here, I'd put 0 down here, I'd put 0 down here, right? But I don't have to write that last 0, right? Because I know at time 0 my position is -5, right? So if I calculate this integral, what am I off by? Well, this -5, right? So if I want to know the position at time 3, I'll write this somewhat p of 3 is really plus p of 5 if I simplify, right? I can subtract p of 5 from both sides, and I get the integral from 0 to 3, p of t, dt. Oh, this isn't p of 5, excuse me, this is just 5. My bad, that's just 5. And then I get plus -5, put the -5 out in front. That gives me p of 3, right? And included with the videos for this week is a way to do this in the calculator, right? So I can do this in the calculator to get the answer, all right? Similarly, I can do this guy and this guy in the calculator, right? And it turns out that this guy, this is the total, not total, I shouldn't say total. This is the displacement of the particle for time, I guess, t between 0 and 3.5. Right, displacement meaning how much has it moved from where it started. And this is the total distance traveled from 0 is less than or equal to t less than or equal to 3.5, right? And this makes sense. The first guy has positives and negatives in it. The second one only has positives. So the first one can kind of go back and forth from positives to negatives. The second one, on the other hand, is always positive, just telling you actually how far you traveled in terms of distance. And you can plug both of these into your calculator to get the answer. Next guy here, how many, we can actually do all of these, and we'll just kind of set them up, because again, we have a calculator. So people enter the line for an escalator at this rate, and we got a function here. So this is how they enter the escalator. And they also exit the escalator at a constant rate of 0.7 people per second. At time 0, there are 20 people in the line. All right, so for A here, how many people enter the line during this interval? Well, if you look back at one of our theorems here that we didn't really talk about, if we're given a rate of change and we want to know the total change, we just integrate from A to B. So we're given a rate of change here. We want to know the total change, how many people enter the line based on that rate. This guy is going to be the integral from 0 to 300 of r of t dt. So, and I just plug that into my calculator, right? R of t is that guy up there. Right, we don't integrate that with any of our rules. That's very complicated. All right. Now, for part B, this is slightly different, right? Part A asks how many people are in the line, how many people enter the line, and part B asks how many people are in the line. And there's a little more we have to take into consideration here, right? So what we have to do is we have to consider how many people we started with, and also how many people are leaving, right? If we want to know how many people are in the line. So this will be the number of people we started with, so 20, plus, all right, how many people enter the line, 0 to 300, r of t dt, and how many people are leaving the line, right? So we have a rate for the people that are leaving the line that we'll subtract. So we have a rate for which they leave the line. So if I want to know how many people we integrate, so 0 to 300, and it's 0.7 people per second, so this is 0.7 dt. And try to simplify these, we get 20 plus the integral from 0 to 300, which we need a calculator for, r of t dt. And then this last guy is minus, and I'll calculate this guy. The integral of 0.7 is 0.7 t, and I go from 0 to 300. Okay, and that's how many people will be in the line at time t equals 100. Okay? All right, part C is a little tricky. Part C is a little tricky. What is the first time t that there are no people in the line for the escalator? And that time is going to be, well, what we do is we figure out how many people are in the escalator, or in the line for the escalator at time t equals 300, which is what this number is. Right, this is the number of people in the escalator at time t equals 300. So we get 200 plus the integral from 0 to 300 r of t dt. And this is just actually minus 0.7 times 300. All right, so that's the number of people, 20, not 200. That's the number of people that are in line after 300, I guess, minutes. Seconds, 300 seconds. That's the number of people in line after 300 seconds. And then no more people get in the line, right? The rate doesn't change. The rate is 0 afterwards, so no more people get in the line. So now the question is, what is the first time there are no people in the line? Well, this is just going to be a number, the answer to this. So I have to subtract the people that leave, right? So the rate at which people leave is we calculated this before. The rate at which people leave the line is 0.7 So if we integrate that, the number of people that leave the line, make this a little better. Oops. The number of people who leave the line is 0.7t. If I just integrate 0.7, I get 0.7t. So I'm going to subtract 0.7t. And I just set this whole thing equal to 0 and solve for t. All right, and remember that this is a number, this is a number, and this is already a number. So there's only actually one t in this problem. Okay? And if you get all that, you get your answer. And we'll go over this on the whole next time we meet. And then I guess we can skip D for now. D's not a big deal for now. All right, and now we look at number 3. How do we do this? All right, so first off, this is a graph of a continuous function whose derivative is shown, right? So this thing up here, this is the graph of g. We have that g is equal to f prime, right? This is the derivative of the function f. The function g is piecewise linear from -5 up until 3. So that means it's made up of lines until we get to 3, and then it has this other function from 3 to 6. If f of 1 is 3, what's the value of f of -5? Well, we use our trick. So if g is equal to f prime, the integral of g is equal to f, right? So if I want to know what f of -5, I can put a -5 down here, right? And I can put kind of a question mark up there. So this is going to be f of question mark minus f of -5. And the question is, what should I put in the question mark? Well, it's the only other f value I know, so I probably should put a 1 up there. Put a 1 up there. Put a 1 up there. And then we could put a 1 over here. Okay? Right, and now we can solve this guy a little bit. We want to get f of -5 by itself. So we have f of -5 is equal to f of 1 minus integral from -5 to 1 g of x dx. Okay, so this is equal to f of -5 is equal to f of 1, which I know, that's 3, minus this integral. And this integral is just area under the curve stuff, right? I'm going to go from -5 up to 1. So -5 up to 1, use a color, is this, I guess, trapezoid. This trapezoid. And up to 1, we would also with this triangle. Okay, so from -5 to 1, that's what we have. The area of this trapezoid, it has height of 3, base 1 of 3, base 2 of 1, 2, 3, 4. So this is 1/2 times 3 times 7. So that's 21 over 7. Yep, 21 over 7. No, 21 over 1/2 times 3 times 7. 21 over 2. 21 over 2. Right, so f of -5 is going to be equal whatever 3 minus 21 over 2 is. So it's what, -15 over 2? Yeah, -15 over 2. All right. Oh, we can skip C, don't care about C. We want to evaluate from 1 to 6 of g of x. Well, that's pretty easy to do. 1 to 3, that area is 4. That's a square with size 2 by 2. And then I need to just do here to here. Right, so to get that, again, I integrate. So I want the integral from, I guess, 3 to 6 of 2 times x minus 4 squared dx. We can calculate this in a few different ways. We can do a u substitution. Or we can just multiply this whole thing out, which I think I'll do. So this is 2, the integral from 3 to 6, x squared minus 8x plus 16 dx, which gives us 2 times x cubed over 3 minus 8x squared over 2 plus 16x from 3 to 6. And if I just calculate this and I add it to my 2 from before, or my 4 from before, so 4 plus this is actually my answer. And that's that for today.